Show that the function f of x divided by 1 plus absolute of x is a one-to-one and onto function. For one-to-one, we'll assume that f of x1 is equal to f of x2, which implies that x1 divided by 1 plus absolute x1 is equal to x2 divided by 1 plus absolute of x2. Now we get three cases. Case 1 where both x1 x2 are positive, case 2 where x1 x2 are both are negative, and case 3 where x1 x2 have different sign. So let's take first case. As x1 and x2 both are positive, we can replace absolute x1 by x1 and absolute x2 by x2. We can simplify this and we'll find that x1 is equal to x2. For the second case, when both x1 x2 are negative, we can replace absolute x1 by minus x1 and absolute x2 by minus x2 and then simplify it, and we find that x1 is again equal to x2. Case 3, when both have different signs. So let's assume x1 as negative and x2 as positive. Because x1 is negative, absolute x1 will become minus x1. We can substitute it and then simplify it. We find that x1 is equal to x2 by 1 plus 2x2. Now we have assumed that x2 is positive. So this implies that x1 is also positive, which is contradictory. Hence x1 and x2 cannot have different signs. And the scenario where x1 x2 were both positive and both negative, that is having the same sign, we found that x1 has to be equal to x2. Hence the function f of x1 is equal to f of x2 implies that x1 is equal to x2, and the function is 1 to 1. For onto function, we have to prove that for any given y belonging to I, we can find an x such that function f of x is satisfied. Now if we look at y, it belongs to range of minus 1 to 1. So we can divide it into two parts, case 1 where y is less than 0 and case 2 where y is greater than 0. Now if we look at f of x, the denominator will always be positive and numerator will have sign positive or negative depending upon x. So that is y will have the same sign as x. So when y is negative, x is negative, and when y is positive, x is positive. So for case 1, when y is less than 0, we can substitute absolute x by minus x and then simplify it to find that x is equal to y upon 1 plus y. For case 2, when y is greater than 0, it implies that x is greater than 0. We can substitute the value and find out that x is equal to y upon 1 minus y. So in both the scenarios, we are able to find out an x given any y. Hence this is an onto function. Show that the function f of x is injective. So we'll suppose that f of x1 is equal to f of x2, which implies x1 cube is equal to x2 cube. Simplifying this, we'll find that x1 is equal to x2. As f of x1 equal to f of x2 implies that x1 is equal to x2, we can say that f of x is an injective function. Given a non-empty set x, p of x is the set of all subsets of x. For subsets a and b in p of x, relation exists if and only if a is subset of b. We have to find out whether R is an equivalence relation or not. Let's take an example where set x is having two elements 1 and 2. So p of x will have null set 1, 2 and 1 and 2 together. Here null set is a subset of all the 4 elements, but the reverse relation does not exist. That is, 1 is not subset of null set, 2 is not subset of null set, and 1, 2 is not subset of null set. Here the relation is not symmetric and hence R is not an equivalent relation. Find the number of all onto functions from the set 1, 2, 3 up to n to itself. Let's take the first element. It can have relation with any n elements in the domain. The second element, the number of possible relations will be n minus 1, as one element has been taken for the first element. Continuing this way, for the nth element, the only possible relationship will be 1. Hence the total relations will be n multiplied by n minus 1 multiplied by n minus 2 multiplied continuing up to 1, which is n factorial. Given two sets a and b and function f and g defined by f of x equal to x square minus x and g of x equal to 2 multiplied by absolute of x minus half minus 1. We have to check whether f and g are equal. Let's evaluate f of x and g of x at all x. So we get f of minus 1 equal to 2, f of 0 and f of 1 is 0, and f of 2 is equal to 2. For function g of minus 1 is also equal to 2, g0 and g1 are same as f0, f1, and g2 is also equal to f2. So from the table we see that f of x and g of x are equal at all x, hence f and g are equal. Let a equal to 1, 2, 3. Then find the number of relations containing 1, 2 and 1, 3 which are reflexive, symmetric but not transitive. The smallest relation containing 1, 2 and 1, 3 which is reflexive, symmetric but not transitive is 1, 1, 2, 2, 3, 3, which gives us the reflexive property, then 1, 2, 1, 3 because we have been given that, and 2, 1 and 3, 1 are coming from the symmetric property. So we see here that it's 1 to 2 is defined, but 2 to 3 is not defined, hence this is not having a transitive property. Now if we add pair 2, 3 to R1, then we will have to also add 3, 2 because we have to maintain the symmetric relation. But as soon as we add 2, 3, it will become transitive, as we can go from 1 to 2 and then from 2 to 3, and we also have a direct relation 1 to 3. Hence there is only one relation which is reflexive and symmetric but not transitive. Let a is equal to 1, 2, 3. Find the number of equivalence relation containing 1, 2. The smallest equivalence relation R1 containing 1, 2 is 1, 1, 2, 2, 3, 3, 1, 2 and 2, 1. 1, 1, 2, 2, 3, 3 is coming from reflexive property, 1, 2 and 2, 1 is coming from symmetric property. Now we are left with only 4 pairs, namely 2, 3, 3, 2, 1, 3 and 3, 1. If we add any pair, say example 1, 3 to R1, then we will also have to add 3, 1 for symmetric relation and 2, 3, 3, 2 to maintain transitivity. Adding this we will get the universal set. Hence there are two equivalence relations.